talk. Okay, let's welcome Yokokura from KO. He will talk about generalized chiral instability in a number and a non-inverse symmetry. So yeah, please start.
Thank you. Thank you for the introduction. And first of all, I'd like to thank organizers for giving me an opportunity to talk in this workshop. So I'm Yokokura from Keio University. Today, I'd like to talk about the relation between the instability and non-invertible symmetries. So this talk is based on this paper. So the message in this talk is as follows. So one of the themes of this workshop is that what kind of the physics can we extract from, using generalized symmetries. So my proposal there is that that is the chiral instability. In particular, the chiral instability can be universally generalized and understood using generalized symmetries. So this is my message. So this is the overview of this talk. So axion electrodynamics in 3+1 dimensions exhibits instability in the presence of the background time-dependent axion or electric field. And the generalized so I would like to propose the notion of the generalized chiral instabilities. So this is a universal mechanism of these instabilities. In particular, the instabilities tend to be weakened, and the magnetic field and the gradient of the axion with linking numbers are generated. And the generated fields can be stable due to the non-invertible symmetries. So this is the context of this talk. So first is the introduction, and next I'd like to review the chiral instability. Then I'd like to explain the instability of the axion electrodynamics in the presence of the background electric field as an example of the generalized chiral instabilities. Finally, I'd like to discuss the relation between the generalized chiral instability and non-invertible symmetry. So the first is the introduction. So I'd like to begin with the gapless modes, so which are modes without energy or mass gap. So in terms of the dispersion relation, the gapless mode satisfies omega equals 0 for k equals 0. So this omega is the frequency, and this k is a wave number. So they are long wave excitation by infinitesimal energy. So it can dominate the infrared physics. In particular, so if so the gapless mode can characterize the phase of matter. So if the gapless mode exists, the phase is called the gapless phase. Such gapless modes are ubiquitous in physics. For example, photon and phonon, or number bosons, and so on. For the gapless mode, the Lorentz symmetry is important. So in the presence of the Lorentz symmetry, the dispersion relation is constrained to the linear dispersion. So in the following, I would like to neglect the higher order terms in this talk. However, in the absence of the Lorentz symmetry, for example, by the explicit breaking by the background fields, there are possibilities of corrections in the infrared region. For example, there can be the first order correction by the frequency. And in this case, we have gapped mode, like this. As another possibility, we can have the first order correction by the wave number. So in this case, we have unstable mode. So let me explain this unstable mode. So we can solve the dispersion relation explicitly, like this. And for the negative beta, so we can find that there is instability in the finite infrared region, in this region. Technically, this is a tachyonic instability with the tachyonic mode, where the amplitude is exponentially growth. So you may think that this instability is just a mathematical possibility, but such an instability arises in realistic systems. So one of the typical examples is axion electrodynamics. So this is roughly a system with an axion and a photon and the topological coupling between them. So the action of the axion electrodynamics can be explicitly written as this. So this is a kinetic term of the axion, and this is a kinetic term of the photon, and this is a topological coupling between the axion and the photon. Since this coupling does not depend on the metric in the spacetime, so this is called topological coupling. Here, this axiom is introduced as a pseudoscalar field with 2π periodicity. And in this talk, so we regard this 2π periodicity as a gauge symmetry because it is a redundancy of the description of the axiom field. Here, a photon is introduced as a U1 gauge field with Dirac condensation condition. And there are other parameters such as decay constant and coupling constant, but I sometimes omit them. So there are several features in the axion electrodynamics. So one of the features is that this is a simple model which are ubiquitous in the modern physics. For example, the QCD axion inflaton and modular fields from string theory and Pizarro method and quasi-particle excitation in topological materials can have this type of coupling with the kinetic term. So, and another feature is that this qubit topological coupling. In particular, this coefficient is determined by the chiral anomaly in UV theory. So in this, this cubic topological coupling is important, and this coupling leads to non-trivial effects. So to see this, we write down the equation motion of the photon and axion, and we find that there are induced current and induced charge and the source of the axion. So let me explain them. So first, I'd like to consider this induced current. So this is so-called chiral magnetic effect. So in the presence of the non-zero axion velocity, this is the time derivative of the axion. So we add the magnetic field. And we have the induced electric current whose direction is parallel to the magnetic field. So this is the chiral magnetic effect. Next, I'd like to consider this second term. So this is so-called the anomalous Hall effect. So we consider the non-zero axion gradient along this direction, and we add the electric field perpendicular to the axion gradient. Then we have the induced electric current along this direction. Since this induced electric current is perpendicular to the electric field, it is different from conventional ohmic current, and this is so-called anomalous Hall current. So next, I would like to consider the electric Gauss law, which is modified by the topological coupling like this. So to see the physical meaning of this coupling, we consider the non-zero axion gradient and the magnetic field whose direction is parallel to the axion gradient. So in the presence of these fields, we have the induced electric charge due to the magnetic field rather than the electric field. Finally, we can write down the axion equation motion of the axion, and this source term means that the electromagnetic field is a source of the axion. So in the following, I'd like to consider this first effect, the chiral magnetic effect, and in the presence of the background axion velocity, we have the instability. So this is the chiral instability, and I'd like to explain this. So first, I'd like to explain the intuitive understanding of the chiral instability. So in the presence of the non-zero axion velocity, I'd like to consider the small fluctuation of the magnetic field, this one. And by the chiral magnetic effect, we have the electric current whose direction is parallel to the magnetic field. Then, by using the Ampere law, we have the induced magnetic field. And this magnetic field further introduces the electric current, and this electric current amplifies the original fluctuation of the magnetic field. So the magnetic field is tachyonically generated. So this is the intuitive understanding of the chiral instability. So how about the dispersion relation? So for simplicity, I'd like to consider the wave number along the x direction. Then the equation motion can be written by this in the momentum space. So we have the first order correction by the wave number. So we can solve this equation, and we have the tachyonic mode in the finite infrared region, this one. Here, this C is the axion velocity. So, okay. So if the wave number is less than the axion velocity, we have the instability. So you may think that this instability is pathological. However, we can show that the instability tends to be weakened because the axion velocity decreases. So let me explain this. So we have shown that the magnetic field is tachyonically generated. However, the time-dependent magnetic field induces the electric field by the Faraday law. And the direction of the electric field is anti-parallel to the magnetic field. So we have the negative E dot B. And by using the equation motion of the axion, we can show that the time derivative of the axion velocity is negative. So the axion velocity decreases and the instability tends to be weakened. And we can further show that the generated magnetic field is stable. So we can show this by using the equation motion of the axion. Since the equation motion of the axion can be written in terms of the total derivative, we can show that the spatial integral of the zeroth component of this current is conserved. Since axion velocity decreases, we can show that the magnetic field with this integral increases. And this spatial integral of A dot B, this one, is an important quantity. It is called magnetic helicity. And this magnetic helicity ensures the stability of the magnetic field due to this conservation law. So there are several applications of the generation of the magnetic field in cosmology and neutron stars. There, axion velocity can be identified as a chiral chemical potential, which is the difference between the right-handed charged fermion and the left-handed charged fermion, or the time derivative of the axion inflaton. So I have shown that the magnetic helicity is important. So what is the physical meaning of the magnetic helicity? This A dot B, magnetic helicity is not gauge invariant, and it is important. So, and I'd like to explain the gauge invariance and the modification of the magnetic helicity using non-invertible symmetry later. Thank you. Okay, so here I'd like to assume that this magnetic helicity will be gauge invariant, but precisely it is not. So let me explain the physical meaning of the magnetic helicity. This is the linking number of the magnetic flux. So for simplicity, I'd like to consider the magnetic flux tube, this one, and we can calculate the this integral in the case of the magnetic flux tube, and we can show that this is equal to 2 times phi 1, which is the magnetic flux on C1, and phi 2, this is a magnetic flux on C2, and the linking number between C1 and C2. And this can be derived by using the Biot-Savart law between the vector potential and the magnetic field. And by using this form, we can rewrite this magnetic helicity in terms of the Gauss linking number. So we have this linking number. So this is the chiral instability. So my question in this talk is how universal is the chiral instability? So there are similar instability. For example, action electrodynamics in the presence of the background electric field and the fourth plus one-dimensional Maxwell Chern-Simons theory in the background electric field. In these systems, we have the tachyonic mode in the infrared region. So my question is that the electric field decrease and the magnetic field with topological quantity increase in these systems. So this is our result. So the decrease of the background electric field and the increase of the magnetic field with topological quantities hold for them. And further generalization is possible. And so I'd like to propose the notion of the general chiral instability. So I'd like to consider the massless Arvinian p-form gauge theories with cubic topological coupling in the flat spacetime in general spacetime dimensions. Then, so there are infrared instabilities in the background electric field of the p-form gauge field. And we can show the decrease of the background electric field and the increase of the magnetic field up to the linear analysis. And the generated magnetic fields are protected by the non-invertible symmetries. So this is our result and the notion of the generalized chiral instabilities. So, but this is, I think this is too general. So in this talk, I would like to consider the action electrodynamics in the presence of the electric field for concreteness. So let me explain the instability in the electric field. So again, I'd like to use the effect due to the topological coupling. In particular, I'd like to use the anomalous Hall effect, this one, and the equation motion of the axion, this one. So anomalous Hall effect means that so in the presence of the axion gradient and the electric field, we have the induced electric current. And the equation motion of the axion means that so E dot B is a source of the axion. So by using these effects, we can show that there is a tachyonic instability in the presence of the electric field. Yes. So for simplicity, I'd like to consider the small fluctuation of the axion gradient. And the direction of the axion gradient is this one, this direction, and this direction, and this direction, and this direction, and this direction. So in the presence of the electric field, we have the induced electric current due to the anomalous Hall effect. And the direction of the electric field, electric current is this one. So by using the Ampere law, we have the induced magnetic field by the electric current. So now we have the negative E dot B inside the sphere and positive E dot B outside the sphere. So by using the equation motion of the axion, the divergence of the gradient axion is positive inside the sphere and negative outside the sphere. So the gradient of the axion is amplified. So the small action gradient is amplified, so, and the magnetic field is also amplified. So we have the tachyonic instability of the magnetic field and the action gradient. So this is an intuitive understanding of the instability. So how about the dispersion relation? So again, we have the first order correction by the wave number. So for yes. Yes. So yes, so for simplicity, I am considering the constant electric field along this direction. Yes, so again, I'd like to consider the wave number along the x direction and the electric field along y direction. Then the equation motion up to the linear order can be simplified in this form. And we have the first order correction by the wave number. And by solving this equation, we have the dispersion relation. In particular, we have the instability in the finite infinite region characterized by the electric field and the axion decay constant. So again, so this instability is not pathological because because electric field decreases due to the amplification of the magnetic field and the axion field. So to show this, I'd like to use the electric Gauss law modified by the topological coupling, this one. So we have shown that we have the magnetic field with the axial gradient. So here, the inner product of the magnetic field and the gradient of the action is non-zero, and here is also non-zero. So we have the induced electric charge. And furthermore, the direction of the induced electric field due to the electric charge is opposite to the original background electric field. The electric field decreases. So the instability tends to be weakened, and we can further show that the generated magnetic field and the action field is stable due to the dielectric polarization. So let me explain this. So we can show that so by using the electric Gauss law, we can show that this electric flux is conserved. So this is just surface integral of the electric field, and this is the surface integral of the dielectric polarization. Here, this S is taken as an infinitely large surface so that we can capture the original background electric field. And we have shown that the electric field decreases, so the dielectric polarization, this one, increases. So the stability of the action gradient and the magnetic field is due to the stability of the dielectric polarization. So again, what is the topological meaning of the dielectric polarization? In the case of the chiral instability, we have the magnetic helicity, and it is related to the linking number. So how about this case? So in this case, we can also show that so this integral is related to the linking number. In particular, the linking number of the magnetic field and the action gradient on the integral surface. So again, I'd like to consider the magnetic flux tube and thin wall of the action gradient for simplicity. On the integral surface, the magnetic flux tube can be seen as 2 points with signs. And the action gradient can be seen as a circle, closed loop. And I'd like to assume that the sign of the action itself changes between outside and inside the circle for simplicity. Then, so if if the circle surrounds either point of the magnetic field, the surface integral is non-zero. For example, so I would like to assume that the action field is positive inside the circle, and this magnetic field is positive. So we have a non-zero surface integral from this configuration. And furthermore, we have a positive contribution from this point. So this is because this magnetic field is negative, and the action value of the action is also negative. So we have this non-zero value from this integral. On the other hand, if this circle does not surround points, the surface integral vanishes because this magnetic field and this magnetic field cancel each other. So if the circle surrounds either point, the surface integral is non-zero. So this is related to the linking number between 2 points and this circle on the integral surface. So we can understand that the generated magnetic field and the action gradient are topologically stable due to this linking number. So this is the summary of the instability in the action electrodynamics in the background electric field. The background electric field leads to instability, and we have the Takeiluk generation of the magnetic field and the action gradient. And the electric field decreases, and the stable action gradient and the magnetic field with dielectric polarization increases. So if you are interested in further generalization, please see our paper. So I have explained the instability in the action electrodynamics in the background electric field. So finally, I'd like to discuss the relation between the generalized chiral instability and non-invertible symmetry. So let me consider the chiral instability. So for the chiral instability, the conserved charge, this is important. So my question is that, so does a symmetry exist for this charge? So this is the converse of the Nathan's theorem. So our answer is yes, but it cannot be an ordinary symmetry. So what is the problem with the conserved charge was a symmetry generator constructed from this conserved charge with a real parameter alpha on the closed three-dimensional space, which will act on the action field as a field transformation. So one of the answers is that so the exponent of the magnetic helicity, this one, is not large gauge invariant as mentioned. So this unitary operator is not physical. So another answer is that so this is just a consequence of the chiral anomaly. So in the presence of the axial photon coupling, the shift symmetry of the axial field is anomalously broken, explicitly broken. So there is no symmetry generator associated with the shift symmetry. So why does the magnetic helicity violate the large gauge invariance? So let me explain the large gauge invariance of the magnetic helicity. So first, I'd like to explain this intuitively. So the large gauge invariance is, roughly speaking, the requirement that the Dirac string should be invisible. So to consider the Dirac string, I'd like to introduce a magnetic monopole, and which is characterized by this surface integral. So on the closed surface, if the magnetic field, the surface integral of the magnetic field on the closed surface is non-zero, so we have the magnetic monopole inside the closed surface. And in the presence of the magnetic field, the vector potential becomes a multivariate function. And to resolve this multivariate function, we introduce the Dirac string. So this is an unphysical magnetic flux to have a single valid vector potential. But the Dirac string is unphysical. So we require the invisibility of the Dirac string. So it is independent of the choice of the Dirac string. However, the magnetic helicity depends on the choice of the Dirac string. So again, I'd like to consider this linked magnetic flux tubes and in the presence of the magnetic monopole. And I'd like to calculate the value of the magnetic helicity. So since the vector potential is not a single valid function in the presence of the magnetic monopole, I'd like to add the Dirac string to have the single valid vector potential. But there are several choices of the Dirac string, for example, this direction or this direction. And I'd like to require the invisibility of the Dirac string. In particular, so this choice and this choice should be identical. However, this choice cannot be equal to this choice because by the continuous deformation of the Dirac string, we have additional Dirac string, which is linked with the physical magnetic flux. And the value of the magnetic helicity changes due to the Dirac string, due to the choice of the Dirac string. So the magnetic helicity is not large gauge invariant. So this is the intuitive understanding of the large gauge invariance of the violation of the large gauge invariance of the magnetic helicity. A more precise statement is as follows. So I'd like to assume that this exponent of the magnetic helicity with a real parameter is a unitary operator. And our problem is that this integrand is not gauge invariant. So we can modify this integral in the gauge invariant form using the source cell by taking the four-dimensional space whose boundary is the three-dimensional space. And in particular, so A dot B can be written in terms of the FF tilde on the four-dimensional space. So we have the manifestly gauge invariant expression, but we have chosen the four-dimensional space by hand. So this expression has an ambiguity of the choice of the four-dimensional space. So we require the absence of the ambiguity of the choice of the space, four-dimensional space. For example, the FF tilde on omega v should be equal to the FF tilde on another omega v prime. And this requirement means that the special the four-dimensional integral on the closed four-dimensional space of the FF tilde should be, with the parameter alpha should be unity. So using the Dirac continuation condition on the FF tilde, we have the condition for the real parameter alpha, that is, this real parameter should be trivial. So this unitary operator with real parameter cannot generate any non-trivial symmetry transformation. This only gives us a trivial symmetry transformation. So this is, I think, the conventional understanding of the violation of the large gauge invariance of the magnetic helicity. However, so it has been found that we can modify the magnetic helicity for the parameter with 2 pi multiple of the rational number. For example, this one with integer q in a gauge invariant way at the expense of the unitarity. So let me review the gauge invariant modification of the magnetic helicity. So we can modify this magnetic helicity using the partition function of the Chern-Simons theory. So this looks technical, but essentially it is a square completion of the square completion of this quadratic form. So by the square completion, we have the q, the q in the denominator can be is in the numerator. So to have this square completion, we should introduce the additional degrees of freedom, and this can be identified as a U1 gauge field on the integral volume with the field strength and Dirac continuation condition. And this modified expression of the magnetic helicity is now large gauge invariant because this parameter q, the integer parameter q is in the numerator. So we have the manifestly gauge invariant expression of the magnetic helicity. So how about the original magnetic helicity? So this is just a naive expression which is obtained by the equation motion only for the trivial Dirac continuation condition. So including okay. So we have the modified magnetic helicity, but in this form the invertibility is lost. So this is because of this is because we have taken the sum of the phase factors. So the single phase factor is invertible, but the sum of the phase factors, such as cosine function, is non-invertible. So due to the sum, the modified magnetic helicity is non-invertible. So by using this modification, we have the non-invertible symmetry generator. So this is action velocity, and we have the magnetic helicity modified by the Chern-Simons theory. So this is a generator of the non-invertible symmetry. So this modification has been done on Omori-san and Yuki Choi and Ram and Shuhei Shao. 大森さん、コルドーさん。Yes.
How about How about the invariance under the 2 pi shift of phi?
2 pi, 2 pi shift of phi is manifest because we have the time derivative on the axiom. The 2 pi shift invariance of the axiom will be important when we consider the non-invertible one-form symmetry. I would like to explain this later. Okay, now the conservation law is manifest by the equation motion of the axiom, and we have the fractional non-trivial fractional rotation on the axiom field like this. And this symmetry generator is non-invertible because this can be seen by the action on the monopole state, and the action of the monopole state can vanish. So in particular, so we have in particular, so the probability is not preserved under the action of the non-invertible symmetry generator. So it is in particular non-unitary operation. So now we can understand the stability of the magnetic helicity as the existence of the non-invertible symmetry. So we have constructed the non-invertible symmetry generator. So one of the questions is that, so is it related to the linking number like the magnetic helicity? I omit the technical detail, but I'd like to argue that the relation between the non-invertible symmetry generator and the linking number of the magnetic flux still holds. And explicitly, we can calculate the expectation value of the symmetry generator in the presence of the magnetic flux tube, and it is proportional to the exponent of the parameter times the magnetic flux tubes and the linking number. So the relation between the magnetic helicity and the linking number still holds in the case of the non-invertible symmetry. So here I have explained the relation between the non-invertible symmetry and the chiral instability. So how about the relation of the non-invertible symmetry and the generalized chiral instability, in particular the instability of in the presence of the background electric field? So more concretely, so how about the relation between the dielectric polarization and the non-invertible symmetry? So again, I'd like to consider this question. So does the symmetry exist for the conserved quantity of this electric flux? So this conserved electric flux is important in the case of the instability in the presence of the background electric field. And our answer is yes, but it cannot be ordinary symmetry. So what is the problem with the conserved charge or the symmetry generator constructed from this surface integral with a real parameter beta, which would act on the Wilson loop as a phase rotation. So this is essentially the Gauss law. So since the Wilson loop is the word line of the test particle, we can consider the Gauss law around the test particle. And we can calculate the electric flux emitted from the test particle using this electric flux operator. And we can find that, so this value is equal to the charge of the Wilson loop. This is unity. So this surface integral is equal to 1. So we have this phase factor. So this is so-called one-form symmetry. So what is the problem in this symmetry generator? So as Suzuki-san mentioned, so the exponent of the dielectric polarization, this one is not compatible with the axion periodicity. Since this axion periodicity is a redundancy, that is gauge redundancy of the description of the axion field, so the observables should be invariant under this periodic transformation. However, this dielectric polarization is not invariant under this two-pi periodic transformation. For concreteness, I'd like to consider this surface integral in the presence of the magnetic monopole. And I'd like to consider the 2-pi shift of the action field. Then this unitary operator is deviated by this surface integral. So in the presence of the magnetic monopole, this surface integral B dot ds is non-zero due to the monopole, and we have non-trivial phase factor. This means that this naive symmetry generator is not invariant under the 2-pi transformation of the action field. So this is a problem. This means that this symmetry generator is not a physical operator. However, we can again modify the dielectric polarization for the parameter with the 2-pi rational parameter. For example, 2-pi over integer in a gauge, manifestly gauge invariant way at the expense of the invertibility, that is unitarity. So to have the modified dielectric polarization, we use the 1 plus 1 dimensional topological field theory. This is so-called BF theory. So again, this looks complicated, but this is square completion, so that Q in the denominator is in the numerator. And to have this square completion, we need 2 additional degrees of freedom. So one is the 2-pi periodic pseudoscalar field, and another is the U1 gauge field with the field strength and Dirac continuation condition. So by using this modification, the 2-pi periodicity of the axion field is now manifest because parameter Q is in the numerator. So this integral is 2-pi invariant, 2-pi shift invariant, and this is also 2-pi shift invariant, and this is 2-pi shift invariant. So this is a modified dielectric polarization. So how about the original dielectric polarization? So this is again a naive expression obtained by the equation of motion only for the trivial Dirac continuation condition. So in the absence of the monopole. So again, so by this modification, the invertibility of this exponent is lost due to the sum of the phase factors. So using this modification, we have the non-invertible one-form symmetry generator. The conservation law is the equation of motion of the photon, that is the Gauss law and Maxwell-Ampere law. And this is one-form symmetry because it gives us the fractional rotation on the Wilson loop, which is the one-dimensional extended object by this transformation. This is essentially the Gauss law. And again, it can act on the magnetic monopole state as a non-invertible transformation. In particular, it can the monopole state can vanish due to depending on the symmetry parameter Q and the surface S. So now we can understand that the stability of the dielectric polarization as is due to the existence of the non-invertible one-form symmetry. So finally, I'd like to mention that the non-invertible one-form symmetry is related to the linking number of the magnetic field and the axion gradient. And we can calculate the expectation value of the non-invertible one-form symmetry generator in the presence of the magnetic flux tube and the thin axion wall. And we can show that this is proportional to the symmetry parameter and the linking number of the magnetic flux and the axion gradient. So the relation between the dielectric polarization and the linking number still holds in the case of the non-invertible one-form symmetry. So this is a summary of this talk. So action electrodynamics exhibits instability in the presence of the background time-dependent action or the electric field. And I have proposed the notion of the generalized chiral instabilities. This is a universal mechanism of these instabilities. So we can extend this mechanism to general maxless abelian p-form gauge theories with cubic topological interaction, such as, okay, so CH FHF of the three-form gauge fields in the 11-dimensional supergravity, and so on. So, okay, so this is the end of this talk. So thank you for your attention.
Thank you, Leo, for your wonderful talk. So any questions? Oh, sorry. Yeah.
Just a small question. Is there such an instability also if you have a chemical potential for massless fermions?
Massless fermions. Yes. So in the presence of the chiral chemical potential.
Yes, chiral chemical potential for massless fermions.
Yes. So
It's
yes.
a little similar to this, but not identical because there is no axion, but still there is anomalies.
In the presence of the chiral chemical potential, we have a similar equation motion for the photon, and we have the instability. Okay. And the coupling between the chiral chemical potential and the photon is derived from Wess-Witten action or something. Wess-Witten action. Wess-Witten action. Yes.
Thank you.
Thank you.
So any question? Oh, please, yeah.
Okay, sorry, only one question I have a doubt because initially you were talking, when you were mentioning the dispersion relations,
Yes.
you were mentioning the Lorentz symmetry, the systems with respect to Lorentz symmetry and Lorentz violating. So in my understanding, those two cases, one is linear dispersion, the other is quadratic, no? I mean, the first system is linear dispersion relation and the Lorentz violating explicitly
Yes.
give you a quadratic dispersion relation. But you didn't mention anything about, well, you showed some series of corrections, I think, or so, of the dispersion relation, but if you could clarify that point, and also you didn't mention anything about the counting of Namu-Goldstone bosons, which is a deep issue in that case, no?
So your question is on the counting number of boson in the case of the no.
Yeah, I mean, that's well understood already. It's 1/2 in the case of Lorentz violating systems, but I noticed that you didn't mention that part, so I was wondering if you didn't care and the other thing is I mean, it seems that you mentioned other dispersion relations, or maybe or you were doing some corrections to those dispersion relations. I don't know, it was at the beginning, the first slide. So I got a little bit lost. So you only consider it's linear and quadratic, right? Linear dispersion relation in one case, quadratic is right.
Sorry.
I'm sorry.
I didn't understand your question.
Well, I mean, in the case where the Lorentz symmetry is satisfied, I want to see if you agree. When the Lorentz symmetry is satisfied, the dispersion relation is linear, no?
Yes.
When it's violated, of course, the tendency is to be quadratic, no? Because there is no space-time symmetry. Yeah.
This one.
Yeah, exactly.
So when the Lorentz symmetry is violated, so we have the gap to quadratic dispersion relation and gapless quadratic dispersion relation.
Okay.
Square root of k. Okay. This one.
Yes.
This one. Yes. So sorry. So what's your question? Sorry.
I mean, precisely because I wanted to see if you were considering other dispersion relations. Of course, there are other types of dispersion relations, but those are the main, no? The main are one linear and the other is quadratic. And the content of Namu-Goldstone bosons with respect to the broken symmetries is different in both cases, no? In both situations. But of course, since you are dealing with some special, with this case of topological phases and so on, of course, these rules might be a little bit different.
そう
Or we can discuss later, it's okay.
そうです、そうです。
Okay, any other question? Okay, so if no further question, let's thank Leo again.
はい